So, we know this. Yeah. So welcome everybody to the second half of this afternoon session. Wonderful conference. So the next speaker is Hironori Oya from the Institute of Science, Tokyo, who will tell us about algebraic study in quantum configuration spaces of decorated lines.
Thank you very much for the introduction, and I really thank the organizers for giving me a chance to talk in this wonderful conference. And this is my first time in Hokkaido, and I'm really enjoying it. Okay. Today I'd like to talk about the quantum configuration space of it. So I will explain what is it, but let me begin with some framework. So let's consider SO2C, and we take some nilpotent radical, that is one. Then this SL2 naturally acts on two-dimensional vector space, and in this case, sorry, this is not correct. So this is you got the stabilizer of 1, 0. Sorry, 1, 0. Okay. Then this G over U plus is isomorphic to the orbit of 1, 0. And this space is literally called the base affine space. And we call the element of base affine space as the decorated flux. Because the usual flux is an element of G over B, but here we consider the over U, so this is going to be what the decorated flux. Okay, so this is the element of decorated flux in the case of the SL2, in the SL2 case. And in my talk, so the genericity of two decorated flux is important. So if a pair of decorated flux, the pair of decorated flux is said to be generic if the determinant of this matrix is not equal to 0. In this case, we call these two pairs are the generic pairs.
Okay, sorry, I meant to give you something. So generic is basically same as linear independent, I guess, right?
Yes,
Okay.
independent in the SL2 case. Okay, and our configuration space is this. So this is the pair of 4 decorated flux, and A1 and A2 are generic, and A3 and A4 are generic. And we divide this space by diagonal reaction. So this SL2 acts on this space in diagonal way. So we consider this kind of space. So this is our Doris space. And so first question is this one. So what is the size of this space? Okay, so okay, so the generic pair of decorated flux, the space of generic pairs of decorated flux is isomorphic to G cross H. So H is the cardinal subgroup, and the correspondence is given in this way. Okay. And this is the inverse correspondence. If we have this decorated flux, then we can recover G cross H in this way. So
What is H?
H is the cardinal subgroup of G. So this kind of.
Is it just 2 elements of GL2? Generic means an element of GL2 and another one?
Yes.
And no conditions across.
Yes.
Yeah, so X1 would go L1, X2 I go some element of GL2. Similarly for X3, X4.
Yes. Sorry, yes, it's true. So this is the middle of generic, and here we consider the pair of generic decorated flux. So we pick out this part, and then, so this part is isomorphic process. So and our spread is this one. So this is the two pairs of flux. So the first part was one, and then the second part was one. Okay. So if before dividing by the diagonal reaction, so this space is isomorphic to G cross H cross G cross H. Okay. So this is isomorphic to G cross H, and this is isomorphic to G.
Or just say G is U plus in this too. G is U plus. Oh, SO. SO.
Yes. Okay. And if we divide this space by the diagonal reaction, we obtain our configuration space, so COM4 squared AG. And so this is actually isomorphic to G cross H cross H. Okay, so we can divide this 1, 1, 1. And the correspondence is given. Okay, so after H1 and H2 are invariant under the diagonal reaction because this H comes from here. So this H is invariant under the diagonal reaction. Okay, so we can bring this H1 H2 here. And if we consider the G1 inverse times G2, then this is the G invariant reaction. So the G invariant with respect to this diagonal reaction. Okay. So the size of this configuration space is G cross H cross H. This is our space. And so this is how to say in some sense of partially generic configuration space. And if we consider generic condition everywhere, then this is actually isomorphic to open double cell times H. So the size, so this generic condition corresponds to this localization. So this is if you consider to fully generic configuration space, then this is isomorphic to the open double cell times H. Okay. And today's goal is this one. So our main question is this. So can we quantize this space in terms of quantum? So this is our question.
Sorry, that was not for two over H. For sure, as you said.
Sorry. Yes. Sorry, I forgot to get it here. Sorry. Yes. And G plus H plus H. Okay. And before moving on to the next contents, let me explain. So what is this? So this kind of space appears in the stereo so in the stereo higher dimensional theory in the sense of Fock interval. So in their equation, we take G as a simply connected larger vector box. And another include is the compact connected oriented surface with some boundary. And in the boundary, we take some margin. So this is called the marked surface. And if we fix the G and the marked surface, we can consider the moduli space of twisted G local systems on this marked surface with decoration. So this is some complicated things, but if we take our marked surface as K-gon, so K-gon means closed disk with K marked points on the boundary. So then this moduli space is actually isomorphic to conf AG. Because in this case, so the disk is topologically trivial. So we don't have any non-trivial twisted zero system. So we only have trivial zero system on disk. So this And this data comes from this decoration part. So the decoration correspond to the decorated flux in the market. So this is simple. So in this sense, so this is our configuration space is the simplest example of their numbers. And if we consider the generic focus, so generic means a genericity corresponds to our genericity condition. So if we consider some generic part of this modular space, then it becomes an algebraic variety. So if we impose a generic condition, then in this case, so we obtain the K cross. So a concave is some generic condition on which and the story, one of the interesting point of this story is this so the function ring on this variety has the structure of a buckler structure. And so, and by using this cluster structure and some Poisson structure, so we can consider the quantization of this space. So this is defined as this is defined in a very algebraic way. I mean, so this is defined as the intersection of quantum, right? So this is as a class algebraic quantization. So we can consider the class algebraic quantization, and my motivation comes from this part. So actually, so this quantization is a bit abstract, and so this we can consider the quantization, but this is somehow combinatorial. So for example, so what's the meaning of quantum cluster variance? So it's a very abstract thing. So and I want to understand this kind of quantization by using the representation theory of quantum. So this is my motivation. And we consider this. Sorry, we consider the quantization of the configuration space in terms of representation theory, and so this is, as I said, this is the simplest case of the modular space, but it should serve as a local piece of this modular space. And so this is the generous boundary surface, and this is the boundary, and this is the boundary point. And if we fix this mark point and take some arc, then we can consider the bond like this. Then we can restrict our local system to this square. Then we can obtain this partially generic configuration space. So this part and this part has some generic condition. Okay, but usually we don't impose the generic condition between these two non-consecutive partitions. So in this way, so the partially generic configuration space appears. And so this should serve as a local piece of the quantized modular space. And actually by using this idea, we can construct in our previous talk, we construct some morphism from this generic modular space to G. So this is called this is called a prism. Okay. And I hope that this algebra, so quantized configuration space, might be related to other algebras. So first one is the so-called plus G scaling algebra. So scaling algebra, in my point of view, so scaling algebra is a quantization of some character variety. And this modular space is a variant of character map. So the quantization of this space should be related to some type of scaling algebra. And in this situation, so for class, scaling algebra should be the yes should be isomorphic to sorry, class scaling algebras for polygon should be isomorphic to so I worked on this. And another algebra is comes from the representational theory of quantum affine algebras. And actually, I previously worked on this kind of rings. So this is called the quantum Jordan ring. So this is kind of the formation of the quantum Jordan ring. And the structure of this ring is described as some concatenation of quantized coordinate ring over unipotent set, unipotent subgroup. And so, yes, this kind of things can be obtained by amalgamating the quantum groups. And so this kind of amalgamation is yes, also appears in this theory. So yes, in this sense, so this is very how to say, not exactly the same, but this kind of things. So it should be related to this kind. So this is my opinion, not the theory. But yes, actually, and this field now generalized after the logarithmic extension of UQN. So this is a concatenation of UQN in some sense. And yes, I think this algebra is related to this. So this is the kind of feature.
Okay, sorry, just want to talk about that, the picture correctly. So this tilted curvy A G sigma is the same on that map G and C A, right? That are they the same thing? I mean, did that?
Yeah. So
Yeah, because okay,
Sorry.
just one shot.
Okay.
This is the other one.
Sorry.
No.
This is my sorry.
Okay. Same. Okay, got it.
So this is configuration space is a local piece of it. This is my okay. And yeah, we want to consider the quantization of this space. And in the quantum setting, we don't have an actual space, but we have we just have a coordinate. So we need to describe this kind of space in terms of the coordinate. So before moving on to the quantum story, let us describe the coordinate ring of this configuration space. It's described in this way. So this is before dividing by diagonal reaction. So the pair of so two pairs of generic decorated flux can be described in this way. So okay. So this is non-zero locus of this function in affine space. So I mean this is an affine algebraic variety, and its coordinate ring is the polynomial localized polynomial rings. So it has 8 variables, and we consider the localization at these functions. And we need to divide by diagonal G action. So we, in terms of coordinate ring, we take the G invariant. So this is the coordinate ring of this configuration space. And in more sophisticated term, so this is this polynomial ring is 4 times tensor product of the coordinate ring, the function ring of base affine. The function ring of base affine space is a polynomial ring in 2 volumes. Okay. So if we consider the 4 times tensor, then we and in general, so the a regular function on the based upon space is isomorphic to the direct sum of the dual of the two representations. So this is the okay. So this we want to quantize this breaking. Okay, let us fix the notation then. Okay. So from now, G is a general simple Lie algebra, not SL2. G is a simple Lie algebra over C, and we that it's quantized, the zero quantized in the algebra, and we worked over the field. And yes, so this bit is a bit technical part, and let W be a wide group of C, and W0 is the longest. So this is the usual notation, and plus is the second dominant integral weights, and for dominant integral weight, we can take the previous weight, highest weight module, so which is only by lambda, and its highest weight vector is by lambda, and the external weight vector is within in W lambda, and the dual of the external weight vector is written as C and W lambda. And if we have a representation of UQ, and if you take a vector from V and vector from the dual of V, then we can consider some linear map from UQ to K. So linear form on UQ defined in this space. So this is usually for established. So this is the standard of this one. And so the dual of UQ has a structure of associative algebra. So which is the dual of the coproduct of UQ. Okay. And in terms of matrix coefficients, this multiplication is described in this way. So C1 V1 times C2 V2 is equal to C of C1 tensor C2 and V1 tensor V2. And here, this I would like to make one small comment, but actually it's very technical but important comment. So here, C1 tensor C2 is an element of V1 dual tensor V2, and we regard this one as the dual of V1 tensor V2 in a natural way. But if we consider this correspondence, then this is unfortunately this is not an isomorphism as a UQ module. So to make it as a UQ module isomorphism, we need to consider the opposite then. We need to consider the UQ module structure used from the opposite. Okay. And in this case, we write this tensor product as tensor bar. So tensor bar means the tensor product module defined from the opposite tensor, opposite column. So, and then this is the definition of quantized coordinate ring. So this is defined as the subspace of UQ dual spanned by the matrix quotient of irreducible UQ, finite dimensional irreducible. Okay. So this is the usual definition of quantized coordinate. And we have the Peter-Waldteich theorem for the quantized coordinate. So this is this one as an interaction of UQ tensor UQ, and as a UQ tensor UQ module, this is whichever Peter-Waldteich. And so we need to consider the quantized coordinate ring of base affine space, and it is defined as some invariant UQ plus invariant part of UQG. So this is good. This means the UQG invariant part. And in terms of matrix coefficients, it is a space spanned by something P lambda. So this part, the right hand, right component is the highest value. So this is quantized continuing algebras. And when we work on this algebra, so we introduce one notation. So this is long. So CB lambda will be written as C system. And from the beta version, we can easily say that OQ of AG is isomorphic to the direct sum of the dual of beta. And through this isomorphism, so the space corresponding to B lambda will be written as O lambda. Okay, so B lambda star corresponds to O lambda. This is our notation. Okay. Then next, we want to consider the definition. We want to consider the quantum analog of configuration space. So the nice definition is this one. So we take the K times tensor product of OQ of AG and take the invariant part. But it has some problem because this naive tensor product is not a UQ module from the quantum. So we need to modify the multiplication. So yes, so this is not a UQ module form. The usual multiplication is not a UQ module form always. So it means that this invariant part is not a subalgebra of this. Okay, so we need to modify the multiplication. So it's a very interesting. Okay. And to explain the graded tensor product, so let me explain one notion. So it's a locally finite UQ module algebra. So what's a locally finite UQ module algebra? This is a K algebra with UQ action. And as a UQ module, it decomposes into the direct sum of finite dimensional UQ module. And unit and multiplication is compatible is compatible with UQ action. I mean, unit and multiplications are UQ module. So, for example, the quantized coordinate ring of G or quantized coordinate ring of AG is an example of UQ module algebra. And the technical point is this. So here we consider the bar tensor because we want to use this time, but it's a technical. Okay, and the graded tensor product is defined in this way. So this is we first take the two locally finite UQ module algebra A1 and A2, and consider UQ. Sorry, so this is considered graded tensor product, and it's as a UQ module, this is just A1 bar tensor A2. And multiplication is modified in this way. So first, we apply the R matrix here. So to switch A2 and A1, and apply the multiplication. So and yes, so R matrix and multiplications are UQ module homomorphism. So this is the UQ module. So this is called graded tensor product. So the multiplication of the graded tensor product is the UQ module. And so the locally finite the graded tensor product of locally finite modular algebras are again a locally finite module. Okay, satisfies some associativity.
So in the process, I guess we just didn't write this tilde or underbar because it's not fixed time.
Even this part.
Yeah.
Yes. Because I wrote here. Yes.
Sorry.
Yeah. Yes. Yeah. I defined this map as a linear map.
Yeah.
So in this case,
So this R underbar is
Yes.
not really underbar. The R underbar
Yes.
on the air function.
are on the bar.
Yeah.
Yes.
Oh, yeah.
Yes, so this is the universal R matrix.
Yeah,
for
that was
opposite
the okay.
So, yes, so this is the R matrix for opposite operands, so I wrote R bar. So if we could use the Brady tensor product, then we can define the configuration space. Naturally. So we consider the k times Brady tensor product of OQAC and take the invariant UQ invariant one. So then, so this is the subalgebra because the multiplication is in. Okay, so this is the definition. Then next question is, how can we study the algebraic structure of this algebra? So this is the main part of this talk. Actually, so the element of this one, this algebra is quite complicated because we took invariant part. So yes, so yes, except for one times one test, so on. So usually, so the element of this algebra is the sum of several terms. So to study the multiplication structure in this algebra, so we need to deal with very complicated sum because yes, so we don't have, I would say, apparently easy element inside this one because we don't get usual invariant part. So the element is always written as a sum of several elements, and so the multiplication of such an element is quite. So how can we study the algebraic structure? And our first theorem is this one. So this is actually a very general. We take a locally finite UQG modular algebra A. So, and we consider this kind of algebra. So we sandwich this modular algebra by OQAG and take a Brady tensor product and take an invariant one. Then this is this algebra is actually embedded in some parts of some extension of the original algebra A. So then, and then this extension is an extension by Cartan subalgebra. Sorry, Cartan subalgebra. So this as a vector space, so AE, so A extended is a tensor product of the group algebra of weight lattice and original algebra A. So this is the this is an yes, extension by Cartan subalgebra. Okay, and this the element of group algebra and the element of A are Q-coupled in this way. But this is almost the original algebra. So our theorem states that if we consider this kind of object or algebra, then it is embedded, extended.
Maybe it's the particular, what is the weight? What's the weight?
Wait, so this is an UQG modular algebra. So we can decompose it by, we can consider the weight space decomposition by the Cartan. And the second point is we have for each lambda plus, we have some numerical element in this space, and it forms an OR set. So we can localize this algebra by some set. So this set, and if you localize this algebra by this multiplicatively closed set, then it is isomorphic to this set. So this one is the isomorphism.
So what is the lowercase b?
All right, so this one.
No. In the fraction, one of it should be Small, I mean.
So this is the determinant of
Okay.
capital. So it's a bit different. Yeah, it's the construction of algorithms we need to understand. Okay. So this is our first theorem. And so we can easily understand this kind of theorem from this isomorphism. So AG, the pair of generic flux, the space of pair of generic flux isomorphic to G cross H. So if we sandwich this algebra by this one, then yes, AG cross AG is attached so on the level of space. And if we take the invariant part, it means that we divide this space by G. So then this disappears. And this H survives. So this H corresponds to the extension by the group algebra. Okay. So if we know this isomorphism, then we can easily understand. So and this localization corresponds to this generation equation. Okay, and one more fundamental property of this algebra is this one. So let us be a locally finite utility modular algebra, and we sandwich this algebra by OQAG and take an invariant part. So we construct this kind of algebra. Then it has a kind of cyclic symmetry. So I mean, we can bring the last component to the first in this way. So we can bring the last component to the first. So yes, actually, so yeah, as I mentioned, the element of this space is always written as a sum of this kind of element. But anyway, so if we apply this map to each summand, then it becomes an isomorphism of algebra. Then we have this kind of cyclic symmetry.
Why does this map preserve invariance?
Sorry?
Why does this map preserve invariance?
Oh, it's we can check it by direct calculation. Actually, so this map is already written in logistic space. And what we check here is this linear map actually gives an isomorphism of algebras. So it is compatible with algebras. It's actually it's a bit untrue. We need some calculation by using survey. Okay. And we want to study the quantum configuration space. So to apply the previous result to the configuration space, we need to set A as the k minus 2 times braided tensor product of OQH. So then, so by applying the previous theorem, we can say that this quantum configuration space is embedded in the k times 2, k minus 2 times braided tensor product of OQAG extended by this story. And if we localize this algebra by lambda, so this is as not complete result. So this is the algebraic structure of the configuration space. So this is the quantum analog of this kind of map. So yes, if you assume that these two are generic, then yes. Sorry, we have a map from H plus AG. K minus 2 times AG. Then we have a map from this space to call AG. So And if we impose the generic condition on the first and last flux, then it will be isomorphic. So this is the yes, and this phenomenon is quantized. So if we consider the localization by this element, then this is that. Okay. And let me explain one more basic structure of this quantum configuration space. So if we have two quantum configuration space, then we can embed these two quantum configuration space in this way. So we can group the K bond and K prime bond along one edge. Good. So, so yes. Then it's theorem is the theorem. So the element comes from this polygon. Q commute with the element comes from this this polygon.
This is sort of a very nice question, but with the power Q, what if the second term is, let's say, again, two terms?
Okay. So this yeah, we embed. Thank you for the question. So we embed these two algebras in this way. So we in the way sharing the vertex one. So the first one is embedded in this way, and second one is embedded in this way. So this is the first one. So and second, this is the second one. So and yes, so yes, 4 correspond to the fourth vertex from the viewpoint of first polygon, but it corresponds to the second vertex from this. Yeah, all yes, all of this polygon. Okay. Okay. Next, yes, we consider the quantum analog of conformal square edge. So this is our goal today. So yes, so there yes, by the corollary, so this so the localized conformal is isomorphic to the tensor square of OQAG extended by quantum. And so what the structure of this algebra? So this is explained in this lemma. So first, so this algebra, so the square tensor of OQAG, and it's actually embedded into OQG, extended again by quantum, a bit differently. And if you localize this algebra by some explicit element, then this is isomorphic to OQG, extended by quantum. So this is a lemma. And okay. So yes, by using this lemma, we construct the quantum grid. So we set the d for lambda as the d lambda, and we consider the 2 times cyclic shift of this element. So this is written as d2. And if we localize, and yes, we have a morphism of this form. So this localized configuration space is morphic to the tensor square of the OQAG extended by Cartan. And by the previous lemma, so we have a map from here to OQG extended by 2 parts. Okay. And but through this morphism, this the lambda corresponds to E lambda here. E lambda here. So if we localize this one, this algebra configuration space by d4 lambda and d2 lambda, then it will become an isomorphism. So this is isomorphic to this. So this is an quantum analog of our previous classical isomorphism. So this is isomorphic OQG extended by 2 quantities. Okay, so as the last part of my talk, let me explain some class algebra. So because the title of this conference is quantum groups and quantum algebras, I explained the quantum group part, and next let me go on to the last part. Okay. Actually, so this partially generic quantum configuration space has a cross algebra structure. So there exists a if we take the double reduced word of W0W0, then we can construct a quantum state associated with this reduced word. And after this is, as well, we do some partially component cross algebra and upper cross algebra. And here, so this extension matrix of cross algebra is the same as the conjugation extension matrix for square associated with the double reduced one. So in this sense, this is the quantum conjugation. And if we take two double reduced words, then these are mutation equivalent. Okay, this is our class structure. And we can construct this sheet by extending the Bernstein-Zerwinski quantum state. Because we have this kind of isomorphism, and this is the Bernstein-Zerwinski fiber for open double Breuer. So, but here the frozen variables are isolated. So we modify this sheet in some way. Then we can obtain the quiver for this algebra. So this kind of thing already appeared in the class. So this is some decorated one. And yes, so this is the frozen variables of this of this cluster algebra. So the first two are the extended carton part, and so this part. So if you know the cluster structure, Bernstein-Zerwinski's composite, so this part and this part are usual. You use your Bernstein-Zerwinski frozen variables, and we modify these variables by some carton part. Then we can put the state associated with this figure. And so the key result to prove this theorem is our previous result. Yes, well, it's a joint work with Fang and Elaine. So yes, actually OQG is equal to the partially compactified quantum class algebra. And partially compactified upper class algebra. So this is yes, the point is we don't invert the frozen variables. So this is very important. And yes, the coincidence with upper class algebra is proved by Fang and Milen. And last year we proved that this is equal actually equal to the class algebra, except for the negative 4. And during this conference, I think two days ago, some yes, a paper appears on outside, and I am they proves that this is working in the case of the day 4. So this is very recently done. Okay, so maybe I should stop here, but let me explain. Let me make some comments on the general case, the general K plus 2 case. So we want to consider quantum cluster structure on this space. And the idea is very simple. So we consider triangulation of K plus 2, and we can find square here and here and here and here and here and here and so on. And we amalgamate them, then we should obtain the quantum cluster structure on this space. And the rough statement is this one. So actually, so this strategy works. I mean, we can group the quantum cluster variables in this way. So if we group the variables in this way, then this, for example, this part and this part and this part are doubly defined. So we need to check the the well-definedness of the growing. And our theorem is, it's actually well-defined. So the point is, the cluster structure for OQ-Conf4 can be considered as growing of two quantum C when I is an unmixed one. So this is the point. Okay. And for two quantum cluster variables on disjoint triangles, Q constant. It's a C. Right, and this is the so so by this theorem, so we can construct a candidate of quantum state. But we still have one conjecture. So we couldn't, we believe that this is definitely true, but we don't know the proof at the moment. So the conjecture is this one. So these variables, the candidate of variables generate a quantum plane in this algebra. I mean, these are algebraically independent. It definitely true. It is true, but we don't know the proof. And these variables consist of these variables are non-zero divisors. And if this conjecture is true, then we prove that quantum configuration space is contained in the cluster algebra string. Okay, I stop here.
Your very first theorem, can you tell us what this map looks like?
Sorry,
The first theorem. Okay.
first this one.
What is pi EA? Can you make this explicit or is this just?
Oh, it's very explicit. Let me think. Yes. So in general, the element of the space is in this space. So and the other comments. And this not fits up this level. So our map this is the modulus of Q A times E or by singular. So sorry, no, so this is the one and I want if I remember to, so the map is for this one. So the invariant, the element of invariant part is always on this one, and yes. So here we have alpha. So if we focus on the element, sandwiched by this element and this element. So this is the dual of highest weight vector, and this is the dual of lowest weight vector. And we focus on the middle part, then and pick up this one with some modification. Then we can get it.
In the last theorem, you have a conjecture quantum class structure. Is that known in the classical case?
Yes, it's true.
By convention or by confusion?
We are by conjunction.
Okay.
Yes.
So in the end, you have to just the quantum seed inside the algorithm.
Yes.
You don't know if the quantum class algebra homicide is working.
But sorry. So I think this is the part of the definition of the quantum seed. So the quantum cluster variables will be algebraically independent. And at the moment, I don't know the proof of this independence. But this is, yeah, actually, yes, as you mentioned, so this is true in the technical critical form. So if we develop if we develop the integral form of this algebra and we study the specialization at critical form in more precise way, then this condition should be true. But now we always work over the some period, so we don't have the specialization at critical form as a point.
More questions?
The quality of A equal to U was with inverted frozen variables or not inverted frozen variables? In the configuration for in the theorem for configuration 4, where you wrote that the algebra,
This one.
this was already with non-inverted, I see.
Yeah, in this picture,
Yeah.
in this picture, so the frozen variable on this edge and on this edge are invertible, but these two are not invertible. So it corresponds to the generation of this one.
I see.
So this part and this part are invertible, but we don't invert this part.
And if you don't invert everything, is it still true that there is no? Then what is what geometric object is behind that if you don't invert everything? Or it's hard to say.
Yes, the very naive expectation is this one. This algebra itself. But I think it doesn't say this last algebra. But I don't know. It's just my impression. I don't know. But yes. It's really complicated.
Any more questions? Understand. We meet in 20 minutes or